Okay, for here we're going to go over these check your understandings. First one we're going to look at number 5. It says the drawing shows plots of the displacement x versus time of three objects undergoing a simple harmonic motion. It's asking which object, 1, 2, or 3, has the greatest maximum velocity. Okay, so for the most part, maximum velocity is equal to angular frequency. I keep saying angular velocity times amplitude. Now, immediately we tend to jump into the which amplitude is greater and try to figure it out from there. But we also have to take the angular velocity into the angular frequency into account, or angular velocity is almost the same thing in terms of it. When we look at the first graph, we find out that the angular frequency is 2 pi over t, or 2 pi times the frequency. If we look at the first one in the amount of space here that's in the dotted line, it completes one revolution in this given amount of time, or keep one complete cycle, and it has an amplitude of a, so the max velocity is about 2 pi a. For the second one, it completes the pattern 3 times in the same amount of time, and the amplitude is 3a. So the maximum velocity is about 18 pi. I kind of got pi cut off. It should be an 18 pi. There we go, 18 pi a. And if we do it for the third one has an amplitude of 2a. The pattern repeats a complete cycle of 2 in the given amount of time. So the velocity is about proportional to 8 pi a. So for this one, yeah, graph 2 would have the greatest velocity. You can also see that if you imagine a particle following this path, it has to cover a lot more ground than any of the other two. In figure 10.13 for number 6, it says the shadow. Okay, so we need to put figure 10.13 here. It's a ball moving around in a circle, and it's trying to ask us where the acceleration will be the greatest. The greatest acceleration will be at its equilibrium points, which is at x equals 0, so it'd be at the 2 points designated with an x. That's it. That's when the acceleration will be equal to 0. That's when the force is changing directions. For number 7, it says a particle oscillating in simple harmonic motion. The time required for the particle to travel through one complete revolution, is the period of the motion, no matter what the amplitude is. But how can this be, since larger amplitudes mean that the particle travels faster? Alright, so angular frequency is 2 pi over t. It does not matter what the amplitude is. The angular frequency will be 2 pi over t. So if we have very wide amplitude or very small amplitude, if the period's the same, they both have the same angular frequency. But a larger a is like having a larger r. An object, when we talked about angular velocity, when an object must move faster to travel the same distance as an object moving in a smaller r. Think of two people running around a track. One person's on the outside area, one person's on the inside. The person on the outside has to run much, much faster to finish running the race at the same time as the person on the inside track. But at the same time, they have the same angular frequency, or angular velocity, which is why their actual velocity is being multiplied by a. So something with a small amplitude and a big amplitude, but the same period, will have the same angular frequency, but they will have different velocities. That's pretty much it for that.